Now let's take a look at some approaches to problem solving. We're going to look at an early approach developed by Neil and Simon. They call the theory of general problem solving. And so imagine it's the 1950s and you wanted to figure out how people solve problems. There's no way at this time to really see how people go about this. Remember, this is sort of in the height of behaviorism, and there's sort of an emphasis on observable actions and observable behaviors. And here, these researchers are actively thinking about how people solve problems, like what's going on mentally for problem solving to occur. And so you could, of course, ask an individual, hey, tell me how you solve problems, but this process would be really slow, a really slow way to gather data. And you might end up with really vague answers because, let's face it, not everybody really has a lot of awareness of how they might solve a problem. Their aha moment, right, they had this insight, was to develop a computer that could solve problems. So if a computer can be programmed to solve a problem, and it does so successfully, then you know you have all the steps needed. And this was really their insight, that if they could delineate all the steps that a computer can follow to solve a problem, then you know you have all the steps, right? If the computer can do it successfully. Now, this approach to understanding problem solving doesn't really determine that the way you program the computer is the same way that humans actually solve the problem. But it does tell you that you figured out how humans can do it. And then you can test with the computer with a variety of problems, and you can test humans with a variety of problems, and you compare the human success and failure rate with the computers. And so you can kind of see if the humans and the computers solve these problems identically and make the same errors, then you can start to get some certainty that, hey, I think you have maybe figured out how it is that humans solve problems. So this was really like the first use of computer modeling to help figure out how cognition works. And so we have Neil and Simon, who we can see here, to thank for that. Now we're going to take a look at the use of heuristics in problem solving. We've already looked at heuristics in this class, but remember, heuristics are general rules of thumb or approaches. And so one type of heuristic might involve creation of subgoals. So maybe you have a big problem, right? And to solve a big problem, sometimes it's necessary to break that big problem down into smaller problems. So let me give you an example here. First off, we want to begin with something that is hopefully a well-defined problem. This is a problem with a clear initial and goal state. Where are we now? Where do we want to be? We saw initial and goal states with the men and elves trying to cross the river, right? But here we're going to apply that same idea to really a variety of different types of problems. We need to have a clear initial and goal state to be able to define this problem before we can really successfully solve it. In contrast, an ill-defined problem is a problem with no clear starting or end point. So let's say we want to decrease the unemployment rate. We want to help people who have had a hard time finding a job get a job, right? And so if that is the case, then let's take a look at whether this is a well-defined problem or an ill-defined problem. Let's start off with the end point. Decrease the unemployment rate. That's kind of vague. Not very clear at all. And there's no initial state. What is the current unemployment rate? So if we want to work on this problem, then we need to create initial and goal states. The initial state is, where are we now? What is the current rate? And the goal state is then what would success be? What rate would be the success, or how many people with good jobs would that be? And then the prospect of good jobs makes us also think about, well, is your goal just to give a person a job, any job, or a particularly better type of job, maybe that has better pay, more job security, benefits, things like that, maybe consistent scheduling, those kinds of things. So it forces us to go from a perhaps important but sort of vague idea to something much more specific. Now, Holyoake suggested that creating a set of manageable sub-problems provides the structure for converting an ill-defined problem into a well-defined one. So what would that look like here for our problem of giving people who need jobs access to jobs, right? Well, it might differ depending on the population. Maybe parents are going to need one approach. Maybe people who are currently unhoused are going to need a particular type of approach. Maybe students have particular needs, and so on. So the idea is that instead of having this very large, unspecified problem, you break it down into smaller sub-problems. And so that might mean separate, sort of initial and end states for different populations of people, different groups of people, or where maybe if you're working with individuals that have obstacles in the way of getting a job, maybe you get them from where they are now to perhaps getting them shelter, and then perhaps other resources, maybe mental health resources. Maybe health care. And then focus on getting them employment. And so we don't go in one step from where the person is now to employment. Sometimes we have to break it down into these sub-goals. Another example might be, how can I help people who don't have enough money, right? Again, a wonderful goal, but it's so vague. And we would need to convert this then into a much more specific problem with what are we talking about here? What is the initial state that we're really trying to address? Is it people unable to afford food and housing? What do we mean by not have enough money? Enough money for what, right? So we would need to define that, and then define what the goal would be. And do that. And then perhaps, and most likely, we'll probably need to also break it down into sub-goals to achieve our ultimate objective, to make sure that people have enough money for the things that you've talked about. Another way that we use heuristics in problem solving, these general rules of thumb, is that we can sometimes solve a problem by applying the solution from one problem to another. And that's using analogies in problem solving. So here is an example of what's called the tumor problem. So suppose you're a doctor faced with a patient who has a malignant tumor in his stomach. To operate on the patient is impossible, but unless the tumor is destroyed, the patient will die. A kind of ray at a sufficiently high intensity can destroy the tumor, Unfortunately, at this intensity, the healthy tissue that the rays pass through on the way to the tumor will also be destroyed. At lower intensities, the rays are harmless to healthy tissue, but will not affect the tumor. How can the rays be used to destroy the tumor without injuring the healthy tissue? Fewer than 10% came up with a solution of reducing the intensity of the rays, but sending them from a variety of angles. So let's say this is your tumor. Then instead of having a single giant powerful ray to destroy the tumor, but then also damage healthy tissue on the way, you have small doses applied from various areas. They all converge on the tumor, and collectively the amount of rays will be enough to damage the tumor, but the rays here where it's passing through healthy tissue are safe enough for that healthy tissue. But so fewer than 10% of people came up with that type of solution to solve this problem. Now, what if before you got the tumor problem, you saw this? Go ahead and take a moment and pause the video and read this problem. All right, so you can see that the military problem here has the solution. And it is analogous to how we can solve the tumor problem. So here we have the fortress with a variety of roads, right, going to it. The general divides up the army into small groups, and they each march up a different road, converging on the fortress at the same time, and therefore able to capture the fortress and overthrow the dictator, right? So a very similar solution. And so the question is, if people are able to see this problem with this solution and then come upon the tumor problem, will they have an advantage in solving the tumor problem using a very similar or analogous type of solution? Well, only about 20% of participants used the dispersion solution for the tumor problem. So even after being given the military story and its solution, it didn't, seem to be enough to really encourage people to use the analogy. Most participants saw no relation between the two stories. Only when told that the military story provided hints on how to solve the tumor problem did more participants start to use the dispersion or convergence solution. So providing information that there are hints in one scenario that could apply to another helps. So that is one thing that helps. Also, giving participants two problems that involve dispersing and then converging help them solve the tumor problem. So more practice with the same type of solution. And we can refer to that type of solution as a solution schema. So how can educators make it more likely that students will apply what they learn in one setting to a different setting? I mean, isn't that, after all, the whole purpose of education, that the information you learn, some of the skills you learn, you will be able to apply to a variety of different contexts and settings later on. So one thing that helps is for students to be explicitly told that one solution may provide hints on how to solve another problem. Also, students need to compare the solutions to at least two problems that share the same abstract solution schema before they can transfer that information. And they need practice with this process, that they're going to be able to use analogies effectively. It's just not an intuitive process for most people.